All right. We looking good out there with the slide?
Yeah, looks perfect.
All right, awesome. So thanks, Tom. That was a great introduction. So I wanted to talk a little bit. Tom and I have done snow ratio work. With it coming into winter season, it was a great time to kind of review some different things. So I thought I'd start with just a little bit of a science review for the upper end of SLR and when to bump those numbers above climatology. So we're going to go through a little bit of work that we did maybe 8 years ago, 10 years ago when Andy was at the La Crosse office. And I also worked with Dave Schmidt, one of our forecasters, on this. So we worked on this and presented at the infamous, I think it was the NWA Madison conference that was canceled, and probably our first taste of virtual presentations there. So let's go forward here. So we're going to look a little bit at extreme snow ratios and what are we talking about there. If we put it into more of a context of climatology and a percentile, we're looking at ratios that are about 25:1 or higher. Like what is the environment that produces a snow ratio that high? So you can see La Crosse there. We have Marty Baxter's climatology, and so our 75th is a 16.7. So, 25th percentile is at least the 90 percentile. And we just wanted to see what kinds of signals there were in the data. So, if you look around, in fact, I'm just going to jump to Tom had shown this page earlier, just kind of the nation, and you can see that the snow ratios really start to increase as you go north and west in the central part of the U.S. and also into the more into the intermountain areas out to the west. So I want to engage our southern offices that while these high snow ratios are less likely, if you see Springfield here, their 75 percentile is about 14:1, and so their tail is a little bit lower snow to liquid ratio. I think the science of this talk will still intrigue you and give you some tools to be at least knowledgeable scientifically when to bump those ratios above your climatology. And then here's just Bismarck's, and you can see their 75 percentile is 18:1. So, their tail is a little bit bigger, so they may be hit with these extreme snow ratios a little bit more. So just kind of going through the microphysics you've all heard about, the dendritic growth zone, maybe takes you back to cloud physics in your undergraduate years. The big thing we're looking at is the -12 to 18 range, Celsius range. And one of the big factors here is also supersaturation. So the more supersaturation you can produce within your environment, and one of the proxies we have as forecast for that is model data, but also vertical motion, right? So the greater vertical motion tends to lead towards more supersaturation over ice crystals, and you get these growth, these stellar dendrites to grow, and basically have the highest ratios that you can achieve because of the way they interlock and the amount of air that's in those dendrites when they start to pile up. So if there's other ingredients, as Tom mentioned, that are important to generating snow ratios. One of them is lighter winds near the surface. One of them is that those crystals, those dendrite crystals, as they fall, aren't rimed or aren't mixed with other crystal growth areas that occur across the spectrum here that you can see on that diagram on the lower right. And you're getting into needles and plates and some of those other different crystal types that may grow in the same environment, and that just acts to dilute the stellar dendrite. So what we did is we just did a study of cooperative data. So these are 24-hour snow ratios. So they're a little bit different from Tom. Obviously, they've got some time to compact. So we looked at 25:1 snow ratios, and we also made a criteria that we wanted to look at events that had at least 3 inches of snowfall. Now, it may be kind of a high bar to set, but we really wanted to reduce the snowfall error. So it reduced our case size overall. But we looked at these 25:1 3-inch criteria cases, and we call them legitimate if they had more than one site. We needed a few sites to validate that this was really one of these extreme snowfall events. And just kind of the flow on the right-hand side of our cases that we had, and you can see they happen in southwest and northwest flow. They're not just a a cold air northwest flow source region type of event. So what we did then is we just looked through the METAR data in that cooperative period and looked for the heaviest snow period so that we knew when that was. And then we just grabbed NAM buffer data. I don't have a sounding site in my forecast area. So what we did is we took some archived NAM buffer data and we just looked at the NAM soundings and we did some composites on those. And we created a proximity sounding that was had those 25 to 1 3-inch reports within about 50 kilometers of the buffer sounding. So it had to have at least 2 of those reports within 50 kilometers. And then we just took those NAM buffer soundings, we looked at the max snowfall, and then we created composite soundings in BuffKit for those events. And we looked at 18 hours leading into the event and 18 hours after it. So I'm just going to show you some results from that study. And I think it brings out the science that you have to consider when you're changing off of a climatology number. And so here we are on the left-hand side. You see 18 hours before the max snowfall. And one of the interesting things that you see right away is the thermal profile is already in the dendritic growth zone from that -12 to -18, which was really kind of interesting to us. The right-hand side on the winds, not the right-hand sounding, but the right-hand side of this first sounding at that 18 hours before max snowfall, you can see that there's a wind shift in place. So we have a frontal zone that's kind of around 825 millibars with that northeast flow source region going on in the low levels and then a wind shift to more of a westerly flow loft. So let's jump to the right-hand side, 12 hours before max snowfall. Again, our temperature profile is staying put, and now we're just moistening, and now you're starting to see the omega signal starting to increase. We're probably to about -3 microbars. The omega menu is up at the top if you're not familiar, but most of you should be familiar with that with BuffKit. So we're at -3 or so, and these are composites, remember. These are 25 soundings all compiled together. And so here now we again see a pretty decent frontal zone in that area and possibly increasing in its intensity in the wind shift. Now let's go to 6 hours before max snowfall. Again, our temperature regime still is hanging out in that -12 to -18 range, and we've actually deepened it a little bit since the last time step. So we've deepened that dendritic growth area, and our omega has again increased now to like -5 as a composite. So if we look at the time of the max snowfall now, we've saturated fully. We're from 600 millibars down through nearly the surface. We are in the DGZ. So we're talking about 350 millibars or so of nothing but dendrite crystal growth. And this is the key, is what is your percentage of dendrite crystal growth in your environment to get towards these extreme snow ratios? And so you can kind of take those and modify them depending on how much dendritic growth you have within your environment. And we'll talk about that a little bit more further in the talk. Here you can see the vertical motions going pretty good, and that frontal zone, a really nice wind shift across the front here with maybe some implied frontogenesis through that area. So let's look at the max snowfall. I'm just going to take some of the ingredients out here so that you can see them. You can see here I've plotted on the right-hand side pressure increasing with height, and then I've taken the relative humidity, and the axis on the top is for the relative humidity, and you can see the relative humidity with respect to ice is super saturated from about 600 to maybe 850 millibars or so. So that's, on that left-hand side, you see that image again that I showed earlier about stellar dendrites. You're super saturated, and you've got lift in that DGZ. And again, I just plotted omega so you could kind of correlate the two together with the -5 omega in the composite. But again, the science is shown, you have some of this microphysics going on in the background, and now you've related it to some of the events that are observed. So a really nice correlation there with some of these more extreme snow ratios. And then just 6 hours after max snowfall and 12 hours after max snowfall, and what you'd expect, you're kind of winding down. You start to decrease the omega, and you start to lose your saturation. And now your entire wind field is basically from the northwest in that whole lower troposphere. All right, so just some summary items here. We've got a deep DGZ we found, usually surface-based, really good lift in the area, super saturated with respect to ice. Remember on Buff Kit, you can look at that by looking at the frost line. That gives you relative humidity with respect to ice. If you turn that on, you'll see if that crosses the temperature profile to see if you're super saturated. Limited snow growth above the DGZ. Because the DGZ is so deep in these cases, you have limited other crystal types diluting the dendrites. And then obviously I said that the entire sounding is colder than -10 to prevent other growth types. And then again, it can be a northwest or southwest flow. So here's kind of a strategy that builds off what Tom said. If you kind of put it into a table, if you will, you start at climatology, and then you try to build scientifically, what are the reasons that I should drop off of climatology or increase from climatology? So some of the ones in the middle column here, we haven't really talked about. We're talking about probably this column on the right-hand side for the talk I just gave, but some things that could decrease you or decrease from climatology would be rhyming, subcloud-based sublimation. You know, you're trying to battle this, maybe an easterly flow that's very dry or northeast flow that's coming in at the low levels, subcloud base, and it's subliming those ice crystals, and that you're getting ice crystal loss, and just doesn't pile up to snow. You'd probably miss your snowfall accumulations in those cases. Melting and rain, obviously, and then what Tom had mentioned here, I have added to that list now with some of that higher QPE. If you're really, you know, you get over like 3/10 in 6 hours, you know, you probably are going to start to pull down lower than climatology. So all those are additive type of features. And then on the right-hand side, like I had mentioned here, a deeper DGZ all the way down to the surface. Again, the whole question is, what other growth types are happening in the troposphere with this storm? If it's a normal winter storm like we see, you're probably with normal climatological snow ratios, you've got all kinds of crystal types going on and crystal growth modes going on. It's just kind of a mixed bag. So to bump above climatology, the deeper the DGZ, the better. And then, as Tom mentioned here, lighter surface winds, obviously crystal fractioning and breaking down when you get winds to blow near the surface. You're just not going to measure as much snow because it's going to settle out. So here's just a case. Here's kind of an exercise for you. I've got 3 cases, A, B, and C. I've got different thermodynamic environments there that you can see, and I've highlighted the DGZ. So on A, I would probably call that a normal winter storm. If I had to give you a climatology for the DGZ for most of our winter storms, it's about 75 millibars deep. There's nothing terribly impressive. Let's assume that the vertical motion is the same for all these. Take a look at them and think about what you do from a climatological value. So on our left-hand side, let's say that that's climatology. What would you do to B and what would you do to C? And I'll just kind of give you a little bit of time to kind of mull over those soundings. All right, so on the far right-hand side, you see the deepest saturated profile within the DGZ. So that should be your biggest bump above climatology. These are pretty straightforward. I'm not trying to you know, throw you for a loop or anything. These aren't difficult. So here's kind of how I would assess this. The climatology, let's say you're in a regime where your climatology is usually about 14:1. As you move from left to right, your DGZ is deepening. You know, you're maybe to 250 millibars in C, and you're starting to slowly bump your climatology or above your climatology for your snow to liquid ratio. Those are the scientific ingredients you have as a scientific basis to start to lift those SLRs, or at least look at the NBM SLRs or WPC SLRs and have a good scientific basis for if they're valid or invalid, so that you can collaborate a change if needed. So just kind of, again, you're modifying off the climatology. Here's just a real quick example. We had a case here in 2009 where it was a northwest flow, you know, situation where the low came out of the northwest here. We had frontogenesis, strong warm advection out ahead of the low. Not atypical for winter time in the northern plains. It was an advisory from all the way from North Dakota through northern Illinois for 3 to 5 inches of snow. And on the right-hand side kind of shows the snow totals that ended up falling here with some 6 to 8s from Waterloo through Cedar Rapids and into eastern Iowa. On the left-hand side, I've just hand plotted some of those snow to liquid ratios. And you can see there's a very narrow swath of 30 to 1, which falls off as you head towards Des Moines, and then it also falls off as you head north towards La Crosse. So if you just look at what the sounding looked like, this is a 15-hour forecast from the NAM back in 2009. You know, it fits all those criteria that we talked about. You got really good vertical motion. You got a super deep dendritic growth zone there, 650 all the way down to the surface. You've got some saturation above that zone, but your omega is dropping off. So your predominant crystal type in this kind of a situation is going to be stellar dendrites. What does it look like to the southwest and to the northeast? Here are the forecasts for Des Moines on the left-hand side. You can see the profiles aren't in the DGZ, or at least only a portion of those are. And it's the same thing for La Crosse up to the northeast. It's a little bit colder. So you've got an isothermal structure to the sounding at La Crosse, and you're saturated. Your vertical motion is less, but your isothermal layer is too cold, and it falls out of the DGZ. And so your ratios drop off. So the models can predict this when you start to get towards deterministic modes, and it does a real nice job. I know many of us have left the SREF probabilities for dead, or the SREF kind of for dead, and in our wake of the HREF, with the HREF coming around and some of the GEFS data out there. But there was some really nice applications that Dave Bright wrote when he was the SU down in SPC, and this is one of them that is still useful. It's the probability that the dendrite growth zone is greater than 100 millibars. And so while I'm not a big fan of 100 millibars, I'd like to see 200, 150, 200, 250. Once you get a really high probability here that 100 is reached, it's usually an indication that it's deeper. So this is just a deprog DT of the event we just looked at. And you can see how it targets that narrow swath of higher DGZ and higher snow ratios. All right, so I'm going to change gears here. So that was a quick whirlwind tour of extreme snow ratios. And if you have questions, keep them. I'll just be able to answer those at the end. But I wanted to kind of switch gears to just give you a quick run through on the snow to liquid ratios in the NBM. This is kind of the I guess the back of the envelope or the dime store kind of presentation here. It's a short and sweet one. I've got a video that I made if you want to, Suze, if you want to show that to your staff. But basically, I just wanted to run through what goes into the snow to liquid ratios in NBM 4.0. So the NBM uses 4 or 5 methods here: the Cobb Technique, the Air Force or Max T Aloft, the Roebber Technique, and then also a thickness technique. This is a picture from Minneapolis. Let's see, it was like in the afternoon yesterday at 3. Way too early for this stuff to be going on. So we'll talk about those techniques briefly, and then we'll just talk about how the NBM snow to liquid ratio is created. So one of the first technique is the Cobb Technique. You're pretty familiar with that, I think. Some of the ideas about the crosshair technique came out of that. But basically, Dan Cobb did some work looking at the vertical motion and the DGZ. And so it's heavily weighted towards that. You get high ratios for the more vertical motion you have within the dendritic growth zone. It's the only technique in the NBM that uses vertical motion. The Max T Aloft method is also known as the Air Force method or Kuchera method. It looks for the maximum temperature in the lowest 500 millibars of the troposphere. So here's the graph that it uses. And so you can see one problem right away, and that is as the temperature falls off, this SLR keeps increasing. And in reality, that just doesn't happen. But you can see that curve there. So what was done is we made a modification the NBM made there was a modification made in the NBM based on some snow to liquid ratio observational data, which I'll get to on the next slide. So here's just a sounding on the left, shows you the max T is about 0.5 in the sounding, and that would correlate to about an 8-to-1 snow to liquid ratio. Really a simple technique. So here's the original plotted snow liquid ratio and max T Aloft in degrees C. And then this is some data from Alaska, and you can see the snow to liquid ratios. First of all, there's quite a bit of variety or spread within the snow to liquid ratios at any one given temperature because of all those different mechanisms that create the snow to liquid ratio in the atmosphere. But what you see there is you see a max right around the dendritic growth zone, and then colder than the dendrite growth zone, like minus 18 or so on the left-hand side of this diagram, you really see the SLR drop off. So the change was made in the NBM max T Aloft version to use this new version, which dropped the curve off to a much more physically relevant scientific curve for applying snow ratio with max T Aloft. Finally, we have a couple more, but the Roebber Technique, 2002, Dr. Roebber in UW Milwaukee was working with neural networks and artificial intelligence at that time. I mean, talk about ahead of the curve, man. So he came up with this Roebber technique. It's only used right now for the GFS and the NAM within the NBM, so it's a very small footprint. But basically, it's a neural network that looks at all these different variables that you see here. The most important ones are the temperature, as you would probably guess, and also the month, the solar input based on the month time of the year. It has its best skill for light snowfall amounts, and it's a measure or a technique that's better than climatology and any kind of a surface temperature method that may be out there. Again, no vertical motion is used for that one. Finally, the thickness technique, really a nice technique from the standpoint of, again, it's simple to do because you just look at the 850 to 700 millibar thickness. And I'm actually surprised at these results. They're pretty darn good. In 2005, Brian Hurley did some work with 63 snow events in the mid-Atlantic. Sorry for any terrain sites that are on this study or high plains sites. But this is all mid-Atlantic snow events, 63 of them. In 2018, he increased them to 103. And you can see those events, and most of them fall kind of around the 10-to-1 ratio. And the highest we see in that whole study was 18-to-1. So again, most useful probably for the normal to slightly above higher snow liquid ratio storms. For the thickness technique, but the correlation is pretty outstanding. 0.9 snow ratio, as snow ratio increases, or as the thickness decreases, that your snow ratio increases, and you can see the points along that curve. So not really a good technique. We don't have any data greater than a snow liquid ratio of 18, but it can really be easily applied to any model, even in the outer periods, the longer forecast ranges. So what does the NBM look like, and how does it create its SLR? So I've listed the NBM component on the left-hand side of the table that you see there, and then the snow ratio methods and how they're mixed. So the NAM 12 and the GFS, which obviously are two components of a larger family of models. You get 33% Cobb, 33 max T Aloft, and 33 of the Roebber technique. So the Roebber technique's used for only 2 models of this entire list, and it's only 33%. So it's a very, very, very small footprint, really, when you look at the SLR. And then you have this class of cams in the middle portion of the table, and there we use a 50% Cobb and 50% max temperature aloft. So one of the items that has been found over the last few years is that the NBM SLR was running hot. So once the NBM SLR is created, it's reduced by 25%. So you got to keep that in mind. My theory is one of the issues with it is these cams and the strong vertical motion that's associated with them on a very small grid scale. And so the Cobb technique using vertical motion may be overestimating the the SLR for those events. So it's a 50-50 Cobb and Max T Aloft, and then some of the larger resolution, lower resolution models that run out to the extended periods give us snow to liquid ratios beyond 3 days, and that uses the Max T Aloft and the thickness technique. So again, these are all blended. You get a number, and that number is reduced by 25% at every grid point in the NBM. But the number's also weighted, so all these models are weighted. So here are the what's called the expert weights in the NBM for snow to liquid ratio. And one of the things you see in this list is that the cams in the first 2 days are heavily weighted. And so any other deterministic model is really just single-digit weighting. These are all percentages. So you see here the cams account for most of the model weighting within the first 2 days, and then that really drops off with time. Once you get to 84 hours and beyond, some of the higher weights are the deterministic models, the GFS, the EC deterministic, which is the ECMWF-D. This is the ensemble mean, the E there. So that's kind of how the NBM snow to liquid ratio models are weighted in time with forecast range. So they're blended together, different techniques, and also weighted according to time. But the bottom line is they use about 4 techniques. Maybe you could cut that down to 3 if you think about how small the footprint the Roebber technique is. All right, so that is those are my 2 talks. I did record this YouTube that does talk about the NBM snow ratios. I think it's like 7 minutes long. It's just a quick run through like I provided here. So you can jot that down or send me an email and I can email you the link, but I'll just leave that on, and I'm open to questions if we have time to do that, Randy.